Bismillah ar-Rahman ar-Rahim. Welcome everyone. Thank you for all the interviewers who have signed up to register. Thanks for everyone here and everyone attended this talk. This is a webinar that is sponsored by IEEE Western Saudi Arabia section and Saudi Council of Engineers, represented by the Electrical Engineering Chapter of the Saudi Council of Engineers. The webinar's title, as you can see here, is the blockchain for decentralized transactive energy management system and distributed electric power systems with renewable energy resources. I would ask everyone here to please mute your mics before we start talking. And of course, at the end of this talk, we'll give time for questions and answers, inshallah. Our speaker is the distinguished Professor Mohammad Shahidehpour from Galvin Center of Electricity and Innovation in Illinois Institute of Technology. And he will, Dr. Ahmed Abdul Wahab is our co-host. He will present and introduce our speaker after I finish this introduction about IEEE and SCE. About IEEE is the world's largest technical professional association dedicated to advanced technological innovation and excellence for the benefit of humanity. Most of the attendees here, of course, know or have heard about IEEE, but these slides will be just as a reminder for us, inshallah. IEEE and its members inspire a global community throughout IEEE's highly cited publications, conferences, technology standards, and professional and, of course, educational activities. The mission of IEEE is that IEEE's core purpose is to foster technological innovation and excellence for the benefit of humanity. IEEE membership is divided or sectioned by geographically into multiple regions, as you can see here. There are about 10 geographical regions, as you can see from the map. We are here in Saudi Arabia in region 8, which includes Saudi Arabia, the Middle East, Africa, Europe, and Russia. And there are about 6 regions only in the States by itself. Which represent, and the membership or the members and the state represent about 42% of the total membership of the IEEE. We also, if you look at the 2 regions here, region 8 and region 10 in the map here, we have about 84% of the total membership of the IEEE, which is higher than the membership in the state by itself. So this is the total membership of IEEE is 422,460 members as of December 2018, which what makes it the largest professional organization or institution. This is the chart that shows the growth of the membership of IEEE since 1963. Started from 150,000 people back then and reaching a little less than 450. Maybe it's even exceeding that number right now. IEEE at a glance, the members are in more than 160 countries, more than 50% of which are outside the United States. More than 123,000 student members, which is a great number of members. 339 sections in 10 geographic regions worldwide, 2,430 chapters that unite local members with similar technical interests, and 3,284 student branches at colleges and universities in over 100 countries. 2,266 student branch chapters, which is different from just the student branches of IEEE technical societies, and 543 affinity groups. IEEE also has about 39 societies and 7 technical councils representing the wide range of IEEE technical interests. More than 4.5 million documents, which is maybe the most, the thing that makes IEEE most attractive to researchers is that it has about more than 4.5 million documents in IEEE Explorer digital library, and with more than 8 million downloads each month. Most of university right now, especially with the pandemic, have made this IEEE library available for free. So I would encourage everyone to get benefit from that. It has over 1,250 active standards and more than 700 standards under development. Publishes approximately 200 transactions, journals, and magazine, and sponsors more than 1,900 conferences in 103 countries. These are some examples of the technical societies within the IEEE. You can find any society that is close or your special field of interest. The IEEE membership comes with a lot of benefits, keeps you technically correct and aware of the state-of-the-art technologies, grows the members' professional network locally and internationally, access to in-person technical forums. IEEE membership also provides members-only discounts and discounts for IEEE products, conferences, and other benefits. It also provides tools for career development and advancement, which is a very useful tool, especially for new engineers, developing critical non-technical skills as well to be for the members to be more effective, and it provides opportunities for senior members to volunteer and give back to the society. There are special interest memberships, which are the memberships within the IEEE membership or general membership. It expands, those special interest membership expands the scope and the depth of the members' technical knowledge. They are specialized in special fields and fields that are close to the interest of those members. It also extends their professional network, influence the direction and application of technology through standards development, and it promotes the entry into the contribution of women programs. These are one of the affinity groups in the IEEE in general. About the Saudi Council of Engineers, the main responsibility of SCE is that as the main responsibility of SCE are setting criteria for and standards of practicing and developing the engineering profession in Saudi Arabia, including licensure terms and conditions, prescribing necessary rules, regulations, and examinations for obtaining professional degrees, preparation and publication of relevant studies and researches, and organizing courses, conferences, and symposium as well. The SCE vision is promoting engineering profession, facilitating engineers and engineering establishments to reach ideal solutions, enhance the performance levels, and encourage innovation and creativity to achieve an internationally recognized position. I'm getting some requests here to annotate, but that's not okay. About the SCE Electrical Engineering chapter, which is our chapter, the goals of the EE chapter is development of professional and scientific fields, as well as the chapter's members, providing members with opportunities to contribute to the scientific and professional movement, preparing professional guides specialized in electrical engineering fields, promoting the exchange of scientific knowledge and ideas between relevant institutions and bodies inside and outside Saudi Arabia, providing consultations and studies to contribute to rising the level of performance in various institutions, and contributing to setting standards for professional practices and professional accreditation. Contributing to setting up training programs that develop the scientific and professional thought of the chapter's members, and contribute to rising the level of engineering awareness in our communities, and representing SCE internally and externally whenever is required. So that's all from our sponsors. I will give the mic now to Dr. Ahmed Abdul Wahab to introduce our speaker, and then we'll give our speaker the presentation to give the talk. Dr. Ahmed.
Assalamu alaikum jami'an, مساكم الله بالخير. Good evening everyone. It is a privilege and honor to present our distinguished speaker, Professor Mohammad Shahidehpour. He is a university distinguished professor, Budin Chair Professor of Electrical and Computer Engineering, and the director of the Robert Galvin Center for Electricity Innovation at Illinois Institute of Technology. In fact, he converted IIT campus to an islandable microgrid. Professor Shahidehpour is the recipient of several technical awards, including the IEEE Burkes Award, IEEE PES Outstanding Power Engineering Educator Award, IEEE PES Ramakumar Family Renewable Energy Excellence Award, IEEE PES Douglas Stanisky Distribution Automation Award. On top of that, he has co-authored 6 books and over 750 technical papers on electric power systems operations and planning. And also he served as founding editor-in-chief of the IEEE Transactions on Smart Grid. Professor Shahidehpour is a fellow of the IEEE, fellow of the American Association for the Advancement of Science, fellow of the National Academy of Inventors, and an elected member of the U.S. National Academy of Engineering. Also, last week, actually, or a couple of weeks ago, we celebrated him being listed as a highly cited researcher on the Web of Science, which means he is in the top 1% by citations, demonstrating significant influence among his peers. Dr. Shahidehpour also is a research professor at King Abdulaziz University, where I have the privilege to work with him on a number of projects. He is the recipient of the 2009 honorary doctorate from the Polytechnic University of Bucharest. With that, I would give the floor to Professor Shahidehpour to amuse us with his presentation. Professor Mohammad.
Bismillah ar-Rahman ar-Rahim. Salam and good evening to everyone, ladies and gentlemen. It is certainly a pleasure for me to be able to speak with all of you this evening. And in particular, I'd like to thank my dear friend, Professor Ahmed Abdul Wahab, who organized this talk, and your colleagues, Professor Al-Qamdi and others who sort of hosted this meeting. So this is the title of my talk, which is Blockchain for Decentralized Transactive Energy Management System in Distributed Electric Power Systems with Renewable Energy Resources. So as it was pointed out, I'm a professor at Illinois Institute of Technology. I operate the Galvin Center for Electricity Innovation. So what I'm going to do tonight is I'm going to divide my talk into 4 different sections. I'll talk a little bit about renewable energy, then I'll talk about the distributed electric power system, talk about the transactive energy, and then finally I will talk about blockchain and applications for making the transactive energy possible. So these are the steps, and then finally I will conclude. So let me start by talking a little bit about Galvin Center. So that's where I'm sitting right now. We are on the 16th floor of the tower, which is located in Chicago. And this is the sort of a floor map of where the center is. And I'm sitting in this corner right here. And we operate the entire campus, which is a microgrid from here. So we have a control room, and I'm going to talk about that. And then we do quite a bit of simulations of this center using RTDS. We also have a tabletop model of the entire campus. So I'm located in this building, and this is a tabletop model where we are able to demonstrate how this microgrid works. So let me start the presentation by this slide, which basically talks about the transformation. So this is the picture of the Edison, and he built the first electric power system in the world back in 1881. And then this is sort of the remnants of that. It's still available in the lower Manhattan in New York City. So there were two things that he did back in 1881 that remains to be very important. The first thing that he did was that he built a DC system. So the power plant that he built was a DC power plant. And interestingly, we are going back to the days of Edison in a sense that we sort of built the AC system afterwards. After he built this DC system, we switched to AC, primarily because AC is a system that you can transmit long distances. So for instance, in your country, if there's a power plant that is, let's say, 100 kilometers away from the city, you generate electricity and then you transmit electricity using high voltages in order to reduce current. So you use a transformer. Those days, they had AC transformers, no DC transformers. So at the power plant, you use a very high voltage, which reduces the current, and reduction of the current reduces R times I squared, which is ohmic losses. Then you're able to transmit electricity long distances. Once you get to the city, let's say to Jeddah, then you again reduce the voltage, increase the current, and bring the voltage to the level that households can use. So in a sense, from days of Edison, we started from DC, but then we switched to AC. But we're going back these days to the DC again, because a lot of power generation is DC. So for instance, the solar PV, that's a DC generation. We use a lot of batteries, those are DC. And also loads are getting a lot more DC because like your cell phone, your laptop, these are all the DC loads. The LED lights that you use in the streets, these are all DC. So there is no reason to use the AC transmission anymore because generation is DC, load is DC, so, and then distances are much shorter. For instance, solar PV is located on the roof of your house and you're feeding power to your building, to your house. So there is no reason to go to AC because distances are much shorter. So that was sort of one important thing that Edison did, and we're going back to that. The second thing that he did and turned out to be very important was the fact that he built a microgrid. And we are going back to the days of Edison and building microgrids. I'm going to talk about that, but microgrids are basically small systems that could be self-sustained. You could island them in case of an emergency. So for instance, your university can be a microgrid. So if the city of Jeddah is out of power, you can still keep the lights on within the university using a microgrid. So Edison built a microgrid, and as you see here, this was a microgrid because there were no grids in those days, you know. So he built this power plant, pulled wires to neighboring homes, and started feeding power. And unfortunately, of course, in those days, only rich people could afford electricity. But now, you know, everybody has access to electricity, at least in modern countries and modern cities, and then they benefit from that. So in a sense, the system that, as I pointed out, we built here, this was a power plant. We use a high voltage transmission, we use the distribution, and we use the load. So the flow of the power was in this direction. So the flow was only from the generation toward the load. But now that we are building these small systems, for instance, if you have solar on the roof of your house can be a generator. So the generation, basically the flow could be in both directions. But of course, this issue of building the solar PV and small generators have their own predicaments. For instance, this is a model in California. California is the fifth largest economy in the world. And then this shows the migration of the solar PV. So these dark browns are solar PV. And then as you see, how much by the year 2025, the state is going to be covered with the solar PV. In fact, as of today, about 50% of the power generation right now in 2020, about 50% of the power generation in the state of California is solar PV. And and this is supposed to grow as we talk more. And let me see if I can get rid of this. The problem that this sort of subject has of the growth into solar PV is that, let me see, is this curve that we call it a duck curve. So this is a daily power production in the state of California. So this is like early morning hours where people are sleeping and the sun is not shining. During the day when the sun starts shining, the thermal generation drops quite a bit. As you see here, the thermal generation during the day drops quite a bit. But at night when the sun is not shining, we go back to the traditional thermal power generation. The problem with this model is that, as you see, during the day, the thermal generation is very low. At night, the thermal generation increases dramatically. So the thermal generation has to be ramped up quite a bit from, let's say, 2 o'clock in the afternoon to 8 o'clock at night. And the power systems are not sort of accustomed to these kind of changes. So if somehow we can take power generation in this area and shift it here or shift it here, we can come up with a load profile that's a lot more flat. And the load profile that's flat has a lot of reliability and a lot of economic advantages. So as we are sort of migrating toward a lot more solar PV generation in every country, including your country, the way we operate and manage the electric power system is going to be extremely critical. Because as I said, solar PV is intermittent, meaning that at night, the sun is not shining, so you're generating a lot of thermal. So if somehow we can introduce a lot of demand response and a lot of batteries so that we don't have this hike at night, it's going to be very important. So that's the subject that I'm emphasizing in my talk, that as we are bringing a lot of solar, the notion of transactive energy and the use of blockchain and the application of microgrid is going to be extremely important. So in a sense, what we are doing is that now we are adding a lot of demand response and the solar power generation in this part of the system. The flow of the power is going to be two ways. Traditionally, as I was pointing out, the flow was from left to right, because here we generated, here we used. But now that we are generating power here as well, in the solar PV, or even in the form of net metering, the flow of the power is in both directions. So the flow goes from the right to left as well. So in that respect, how we manage this system in this new sort of a new paradigm is going to be extremely important. And that's a subject that your country, I'm sure they're paying attention to that, but it's going to be much more important because your country is very ripe for generating solar PV and renewable energy. And as you introduce solar PV and the two-way flow of the power, introducing these issues that include the grid reliability, the economics of the system, and the environmental mandate gets to be a lot more important. So in order to do that, and this issue has been also of importance to your country as well, this is the way we traditionally operated the electric power system in the form of silos. So this was utility A, let's say city A in your country, city B, city C. Each city or each utility had its own generation, transmission, distribution, and the load. So CDA and CDB and CDC really did not do much with each other. It's CD generated, transmitted, distributed, and then used the load. There could be some transactions as far as sharing for reliability purposes. For all practical purposes, each city had its own operation. The problem with this model is that these small generators could be solar PV or let's say small gas generators could not participate. So let's say if you were generating solar on the roof of your house, or if you had a small generator, you could not use the transmission and distribution, at least in the United States, because these transmission and distribution wires were owned by Utility A. And Utility A did not allow these third parties to come and use these wires. So although we sort of started bringing in a lot of distributed generation and the solar PV, but there was no way for these guys to reach the load because the transmission and distribution wires were monopolized by Utility A or Utility B or Utility C. So what they did was that in the United States and many other parts of the world, including your country, they restructured this electric power infrastructure. So rather than using vertical integration, they went for horizontal integration. So horizontal means they put all the generations together, all the distribution generation together, and all the loads together. So here it was generation, here it was transmission and distribution, and here it was load. So at this first level, all the generators could compete with each other, whether it was a very large generator or very small generator. And then the transmission and the distribution was managed by central authority, like what's done in your country. And then they decide how the load was going to be supplied. So the load here could be supplied by this plant or this plant or this plant. So this transmission and distribution authority managed the way load was supplied. So by going from the vertical integration to horizontal integration, you allow these small generators, which could not participate originally, now participate in supplying the load. So that was one way of bringing this notion of small generators. So as I pointed out here, when the power was generated here and the power was generated here, the flow of the power in direction allowed these small guys to participate as well. However, as I pointed out, this notion of distributed generation and distributed renewable energy had its own problems. I talked about the duck curve earlier, but this is another example of that, in particular when you have load. So let's try to consider, first, we don't consider any renewable generation. And because of that, the load gets to be cyclic. So this is load for, let's say, Monday, this is the load for Tuesday, this is the load for Wednesday. And as you see, they repeat themselves. This is the sort of a load. So they repeat itself. And this is the morning peak, evening peak, morning peak, evening peak, and they repeat themselves. Now let's introduce some renewable energy. So what you see here, this is renewable energy that's introduced in the green color. And then as you see in this case, wind energy is not cyclic anymore. So some days you have a lot of wind, some days you don't have wind, and then it varies on a daily basis. So if you treat this wind energy as a negative load, subtract that from the traditional load, what you get is a net load. So net load is this dark, thick color, blue color load. So this is the net load. Where the net load is the difference between the traditional load and then what you supply from with the renewable energy. The problem now is that, as you see, this net load is not cyclic anymore. Sometimes it gets to be as low as this much. Sometimes it increases this much. It's not cyclic anymore. And again, this creates a lot of problems for the dispatch systems to operate when the load is not cyclic, because when it was cyclic like this, it was very easy to forecast the load. So if you had forecasted, let's say for Monday, it was easy to forecast it for Tuesday and Wednesday and all that. But now when it gets to be like this, which is not cyclic anymore, it is very difficult to forecast the load. So as I pointed out, as we are bringing a lot more scarcity and uncertainty into the electric power system, the way we operate the grid gets to be very, very important. That's why the notion of transactive energy and microgrids and the notion of being able to use a lot of storage and battery devices gets to be very, very important to make sure that as we sort of migrate to this kind of operation, we can still operate it on a daily basis. So in order to do that, we start introducing a term called transactive energy. So basically, here we divide the system into two parts. One is the distribution part, which includes all the low voltage systems, including storage devices, residential, presumers, which are producers and consumers, all these systems, microgrids. So what we see up here is a low voltage part of the system. Then what you see down here is a high voltage transmission. So we sort of segregate, we sort of divide these two parts of the system, and we call them the transactive energy systems in order to be able to manage that. So on the distribution side, these guys talk to each other. So if you have a storage in the back of your house, in your basement, you can sell power to your neighbor. And then if your neighbor is a presumer, which is both producer and consumer, they can sell power to commercial buildings. So at this level, these entities talk to each other. And they're managed by a distribution system operator. So there's an operator here that manages all the low voltage systems. And then there is also an operator at the transmission level, the way it's available now in your country. So this transmission entity buys power from generators, buys power from large renewables, and manages the system at the high voltage. Then at the low voltage level, if they see that there is a shortage, then this distribution system operator contacts the transmission operator and buys power. Likewise, if this low voltage system has excess power available, makes it available and sell power to transmission grid. So these entities communicate with each other, buy and sell power in order to manage the system. So that's the transactive energy that's managed at the distribution level, and it's managed at the high voltage transmission system, and these two systems communicate with each other. So the transactive energy, which basically refers to end-to-end techniques for managing the generation flow and the consumption of electricity in the electric power system, as I said, divided into two parts on the distribution side and on the transmission side, has a number of advantages. One is that it allows distribution decision making. So here, the decision making is done at the distribution level. So if you have a storage device, you can sell power to your neighbor. If somebody is generating power on the roof of their house, they can make it available to the neighbors again. It encourages the consumer role. So traditionally, this consumer side was a passive system. They did not do anything. Whatever was generated here, you just buy it without having any role into how this power is generated, how you can change its paradigm, how you can shift the generation, what the demand response is. The other thing that the transactive energy does, it is an end-to-end coverage. So here, basically, you generate, you consume. Here you generate, and then you make these two systems to each other. The challenges that exist is that, for instance, the wholesale locational marginal prices now have to deal with the distribution locational marginal prices. We have to worry about the distribution flow charges. You know, at the high voltage transmission level, people pay when there is a flow charge. Now we have to also worry about that at the distribution level. And also we have to worry about the congestion. Traditionally, we worried about the congestion at the transmission level. Now we have to worry about that too. So as we migrate towards participation of the load and in the form of both generation and consumption, we also have to worry about some of the issues that traditionally did not exist. It was confined to the transmission system. Now we have to consider here as well. Well, it's a great idea because as we introduce this transactive energy, you allow consumers to decide not to use that much electricity late at night, or let's say 8 o'clock at night, shift non-essential loads to after midnight so that we don't have to have so much generation at 8 o'clock at night, make the light generator to come in and generate so much at night and then generate electricity using fossil fuel-based generation. One way to implement this transactive energy that I was talking about is the implementation of the microgrids. Again, a microgrid, as I pointed out, these are small neighborhoods or even small universities or large university like yours. So in this case, this is a microgrid. This could be another microgrid. And these are interconnected to other microgrids, and they're all connected to the local distribution system. For instance, this microgrid number 1, it could be KU. It could be the King Abdulaziz University located within the city of Jeddah. But one university is a microgrid. And then within that, you could also have some nanogrids, which could be smaller buildings, like your hospital within the university could be a nanogrid, which is a critical load. And all of that are connected to others. So in this respect, each microgrid manages its own operation. In case the city is disconnected, in case some parts of the city are disconnected, we make sure that the KU remains in operation all the time in the form of a microgrid. So what are the advantages of these microgrids, which use a lot of renewable energy? They use a lot of, let's say, small generators or the battery storage. They also could use a larger power plant. So in a sense, when you have a microgrid, you are in charge of your destiny. How you would like to generate electricity, how you would like to consume electricity, whether the university or critical loads, which are called nanogrids. So here, microgrids would allow you to locally integrate renewables and other distributed generation sources and provide reliable power to consumers. So here you decide what does reliability means within the university. You decide how you're going to manage your load, manage your distribution system while you're connected to the city, but you are in charge of your system. So in that respect, you can protect critical infrastructures. So if the critical infrastructure within the university is your hospital, is, let's say, office of the president, is your data center, in the form of nanogrid, you can manage this. And this protection can go on as long as there is a threat for both physical or cyber disruptions. This microgrid allows or ensures the critical operation can be sustained if this outage is prolonged. So what it means is that if this outage goes on for a number of days, so if the city is out of power, let's say for 5 days because of cyber threats or the physical threats, the university can be managed as a microgrid. So university can stay on, can be managed as a separate node, and this sort of can be prolonged as long as the city is out of power. So basically what we're talking about is the grid of the grid. We're not talking about getting rid of the local distribution systems. What we're talking about is to divide the city or divide the loads within the city into different microgrids to the extent that each microgrid can be managed individually. So again, the generation within each microgrid could be renewable, could be traditional fossil. You decide what kind of generation you want. You decide what's the critical load, and then you decide whether or not you want to introduce demand response. So this microgrid is a building block of this smart grid, which includes the distributed generation. So let me give you an example of this microgrid. As it was pointed out earlier, we have converted the entire campus of the university where I work to a microgrid. So this is the footprint of the university. This is the university's microgrid. This is downtown Chicago. And this photo was taken from my office looking north. So all of this is the microgrid, which is shown here. So this it's not a large university. My university is a technical university, which includes 52 buildings, which you see here. And then we have divided this microgrid to 7 loops. So for instance, this is loop number 1, which includes number of buildings. This is loop number 2. This is loop number 3, all the way to loop number 7, where my office and gas center is located. And each loop, for instance, if you look loop number 1, as I pointed out, it encompasses certain buildings, and it's connected to north substation. So university has 2 substations. This is the north substation. This is the south substation. Each loop is connected either to the north or to the south. And then we have a number of Vista switches. These are small circles that you see here. These are Vista switches. And then we have different types of generation throughout the campus. So in case of an emergency, we can open the switches at these two substations, which we call it the point of common coupling. The entire campus will be islanded, and then we manage the system. So this is the electrical distribution. As I was pointing out, this is the north substation, this is the south substation, this is the utility grid. So power comes in at 12.47 kV. It's downgraded to 4,000 volts, 4160. So the entire campus with the 7 loops is managed by as a sort of islanded microgrid once you open the switches here at 4160 volts. So these are the individual loops. As you see, each loop has its own building. It comes with its own solar PV generation. These are the Vista switches, and it's a loop, as you see. So the good thing about the loop is that if part of the system is not functional, for instance, if this cable is broken, I can still feed the building from the other side. So we never lose power using this model. And then there's a normally open switch between the two substations. If one of the substations is malfunctioning, I can close the switch, and the entire campus will be supplied by the second substation. So it's a great system. Ever since we built this microgrid, we have not had any downtime. We've had outages, but no downtime. Basically, lights never go off in this system. We saved the university about $1 million annually. Imagine if this system of 12 megawatt can save $1 million annually, how much you can save in KAU or in the city of Jeddah or the country of Saudi Arabia by converting the system to this microgrid. So for instance, these are different components. We have a wind unit on campus. We also have a charging stations. So this is about 20 kW of solar. It's a solar canopy that supplies these charging stations. So all the utility cars on campus are electric, EVs. So they go here and get free charges. And of course, this charging station is connected to the rest of the campus. So if it's a cloudy day, then we provide electricity to the charging stations using the rest of the campus. But it's a great technology because we don't have to pay for the fuel for the utility cars. They go there and get free charges. And also the charging station is used by professors and students to some extent, as much as possible, for using electric cars. And as I was pointing out, this is the tabletop model of the microgrid. This photo was taken earlier from this building where my office is, and these are different loops. So the colors show different loops. And this is the campus power plant. And then if you visit us, we can demonstrate here how the microgrid works. So we also have a control room here for the microgrid, again located at the Galvin Center. As you see, nobody's sitting here because the entire system is automated. But for the control people who sit here, they monitor the system. For instance, this is the campus microgrid. These are individual buildings. For instance, this is one of the buildings. So it shows how much solar we are generating, how much we are pulling from the grid, how much battery we have, what's the building load. So this is one of the buildings, it's a Keating Hall. So the system operator has control over the entire building. They know how much solar we're generating, how much load we have. And in case of an emergency, they know how to manage the local grid. So that's the benefit of microgrid that allows you to manage the system in case of an emergency for resilience purposes, and in a normal day when the sun is shining for economic purposes. So this is the model of this control system for the microgrid. So this is the master. So it's divided into 3 components. This is the master controller, this is the building controller, and the sub-building. So master controller up here receives the signals from individual buildings. So individual buildings are managed by a building energy management system manufactured by Siemens. So Siemens has a building energy management system, all the 52 buildings. So provide the daily load profile to the master controller. You also get the data from individual generators, from the batteries, and also the campus grid. All that information goes here in the loop-based microgrid, And this master controller, which is basically a software located at our center, it does a day-ahead scheduling. So it figures out for every hour in the next day, what's the best way to manage the grid? Do we need to import power from the local distribution system? Do we turn on our local generation system? How much solar we have? How much battery? When do we charge and discharge the batteries? Whether we can do any demand response in individual buildings, all that information is decided here in the day ahead. And also in real time, every 10 minutes we do corrections. Because as you know, the solar could change in matter of seconds. Clouds can show up. So even if we come up with a day ahead schedule, in real time we have to adjust that. So every 10 minutes, this master controller looks at the amount of solar generation, wind generation, battery power, and actual load of the building, and then do correction. So it's a great system. And then interesting, this system was introduced by PhD students. As I pointed out, we have about 50 PhD students, and they are the ones who participate in the design of the system. A lot of projects that we also do here at the Microgrid was done in collaboration with KAU. I work closely with Professor Ahmed Abdul Wahab and Abdullah Abu Surah, and then the three of us have done quite a bit of work that has culminated in the operation of these microgrids. We also have several nanogrids at the university. So as I pointed out, nanogrid is confined to one building. So microgrid is a whole campus. Nanogrid is, in our case, confined to one building. So this is one of them. And we call it the AC-DC nanogrid because the building encompasses both. So this is the 220 kW on the roof of the building. The building is called the Keating Hall. So this is the model of the building. It has two loops. One is a DC or a DC bus, and then also it has the AC bus. So all the DC loads are connected to the DC bus. All the AC loads are connected to the AC bus. And then this is the 220 kW of the solar on the roof of the buildings. As you see here, these are all the solar PV arrays. Some of it using a DC-DC converter are connected to the DC bus. Some of them using a traditional DC-AC inverter connected to the AC bus. So both buses are supplied by the PV. And also there is a bidirectional converter that connects the DC bus to the AC bus. So if one of the buses has excess power, for instance, if the DC load is less, that excess power could be transferred to the other bus. And then we have batteries all over. So this is the operation of the system. So this is the solar PV generation, the 220 kW. The red is the load of the building. So as you see, when the gymnasium, Keating Hall, which is the sporting center, when they open in the morning, the load keeps increasing because people go there to exercise. Well, even at the peak, we have excess solar power generation. And then we take this solar power generation and put it in a battery. And then we are able to turn the lights on at night using the battery. So it's a great technology where we do a demand response, and then we save about 25% of the system using this technology. So this is the model. This is before and after. So as you see, these are all the LED lights within the sporting center. So these LED lights, which are DC. So this DC load is basically the LED lights, which are fed from the DC generation. That's why this whole system is very simple. That's why I was pointing out earlier that if your generation is DC, which is the case here, and your load is DC, which is all the LED lights, then you can build a very simple DC system and feed the load. That's why this is called the AC-DC nanogrid, because part of the system is DC, which is this one, and part of the system is AC, which is down here. And then the two systems are interconnected. So in case, and then this building, the entire building connected to the rest of the microgrid. So in case of an emergency, I can open the tie and island this whole building and then manage the system as an island. So this is island within the island. So the microgrid, the entire microgrid is islandable. And this is a nanogrid that is islandable. So that's the beauty of this sort of system, distributed system that we have built. We can island buildings, we can island the whole campus, we can decide how the load is managed, we can do savings, we can manage the resilience of the system. So it's great technology that hopefully it will be implemented at your university as well. So this is the summary of what we have at our microgrid. So this is a microgrid. This was the AC/DC system that I showed you. We are installing a flywheel at the university for the control of the frequency. We have converted all the LED lights, all the lights on the campus to LED. This is the new one. You see how bright it is. This is the old system of high pressure sodium. So again, these LED lights on campus, street lights on campus, this is DC load. So it can be fed from the DC generation. This was the charging station I showed you. These are LED lights. This is our latest, the Crown Hall converted. So it's like a park. If you visit us, we can show you different technologies that are implemented at the university. I want to talk a little bit about this Bronzeville technology. Oh, before that, I also point out that I spend about 30% of my time traveling. I travel your beautiful, I go to other parts of the world as well. And then I build microgrids. For instance, this is one of the microgrids I built. This is in the US Virgin Island in the southern part of the United States. This is in Africa. This is in India. So these are some of the poorest areas in the world in India. So these people have never had access to electricity. So we work with Panasonic. We have commercialized this technology. So local people go and put a small solar PV generation on the roof of these shacks where people live. And then these small systems keep the lights on at night, and also allow these people to use cell phones. So very simple technology that we help people, because as of today, about 1 billion people with B, 1 billion people in the world have no access to electricity. People live like this. So what we do is that the technologies that we have developed in Chicago, we sort of use them in order to help people in other parts of the world. So we have projects in India, in Africa, in Central America, in some parts of Asia. So I travel quite a bit, and then I do this kind of work free of charge. One of the things that this was here, I said I want to talk about that, which is the notion of multi-microgrid. So we are building multi-microgrid in Chicago. So what does it mean? This red is the university microgrid I was pointing out earlier. The blue or the black is the second microgrid that's being built by the local utility. So these two microgrids are interconnected. That's why I call it a multi-microgrid. So right now we have two microgrids, someday could have more. So what it means is that our university is about 12 megawatts. This part of Chicago is about 10 megawatt. So in this area, you see about 22 megawatt of the load in the form of microgrid. So in a normal day like today, when the sun is shining in Chicago, we do our own microgrid operation. We do demand response, we operate nanogrid, we do whatever we need to do. And this part of Chicago will do its own thing. There is no interchange between the two systems. It could be for economic purposes, but basically we do our own, they do their own. However, in case there's a local outage, if the city of Chicago is out of power, then these two systems will be islanded and interconnected. So there is a 12 kV underground cable, dedicated cable that connects these two systems. You can see it here. This is a 12 kV cable that connects IIT microgrid to the Bronzeville microgrid. And then these two systems now are islanded, and then we can manage our own load and then help this system. So this part of Chicago has critical loads because Central Police Station for the city, Central Fire Station, some of the high security buildings are located here. So it is very important for the city to make sure that the lights always stay on here. So by interconnecting these two microgrids, building the multi-microgrid, we can do that. we can curtail non-essential loads and feed power here. That's why it's called a multi-microgrid. So not only are we able to keep the lights on in our own system, we can save electricity using our own neighbors. So we work with different entities. We work with Quanta, SNC, Schneider, Alstom, as I said, Siemens. We also work with entities like Microsoft, OSI Soft, Argonne National Lab. A lot of entities participate in building this. So it's a multifaceted operation that shows how large cities could be converted to multi-microgrid in order to save the system and enhance its economics, enhance its resilience, enhance its reliability, enhance its security, enhance its sustainability. So for those of you who have taken some control courses, here I want to show the frequency response of the system. So this is the root locus of the system, basically the frequency response. As you know, when we plot the root locus, the frequency response, the system is stable if all the open loop poles are on the left half plane. So this is the zero axis. So anything that's on this side of the zero axis is stable. Anything that's on this side of the zero axis is unstable. So in this case, as you see, for one microgrid, some of the poles are located on this side, on the right-hand side of the zero axis. So the system is unstable. So, but when you build this multi-microgrid, the coordinated operation, now you see the zero axis is here. So I've shifted everything to the left side. So I've converted the unstable system to stable system. So that's a great advantage in the sense that when two systems are operated independently, there was a problem as far as being able to stabilize the system. But once when they operated in an island, but once I put the two islands together, as you see here, I'm able to stabilize the system. So it's great advantage of building these multi-microgrids, not only from economic point of view, but from operations point of view, from a reliability and resilience point of view, and enhance the operation of the system. So how do we make these microgrids talk to each other? So if you have, in general, when you sort of build additional microgrids, if it sort of metastasizes, let's say in this case you have 4 microgrids, microgrid 1, microgrid 2, microgrid 3, and 4. In this case, this DSO, the distribution system operator, is the operator of the grid. So in this case, if microgrid 1 wants to talk to microgrid 2, they will have to do it through DSO system. So there is no direct interconnection between these two systems because the wires are owned by the local distributions company. However, once we switch to transactive energy, then these microgrids, the transactive energy I was talking about earlier, then now in this case, these microgrids can talk to each other. 1 can talk to 2, 2 can talk to 3, 3 can talk to 1. So from the economic point of view, these guys can transact energy. However, DSO is still needed because the control of the wires are still managed by the DSO. So in case microgrids solely interact with the distribution system operators at the fixed electricity cost and this system. But when we build this transactive energy market or TEM, then in this case, from a P2P or peer-to-peer operation, microgrids can directly and flexibly trade energy with each other through dynamic market signal. So in this case, microgrid 1 can buy power from microgrid 2, and microgrid 2 can sell power to microgrid 4, and then all these transactions can happen. So in this case, they do transactions for economic purposes, but then DSO, which is in charge of the owner of the distribution wires, it has to come in to make sure that these transactions are possible. So transactive energy is a great thing that allows these entities to talk to each other. So it doesn't have to be microgrid. For instance, this could be one house, this could be another house. Then they can transact energy. For instance, if house number 1 has a solar on the roof of the house, and house number 2 has a EV car, the electric vehicle. So then this Microgrid 2, which is basically the EV owner, can buy power from Microgrid 1, which is a PV solar owner. So rather than for Microgrid 2, rather than going buy power from the local distribution company, it buys power from the neighbor. So they do transactive energy, one buys, one sells, and then the sort of a transaction, the actual physical flow of the power will be managed by the DSO. So the operation is done at two levels. At the lower level, you have the transactive energy. As I pointed out, these microgrids talk to each other, and then they transact energy, they buy and sell power. Once these agreements are made, who's going to buy, who's going to sell, that information is transferred to the upper level. And the upper level is a DSO, which manages the network. So all the wires are owned by the local distribution company. The local distribution company does not know who's buying, who's selling. All it knows is where the source is and where the sink is. And then the DSO makes that possible. So DSO will do the network reconfiguration in order to make these transactions possible. And then if the network reconfiguration does not allow these transactions to occur, then this DSO will send a signal in the form of trading adjustments to the lower level. So we send the equivalent load to the upper level. The DSO will do optimal power flow. It figures out where the transactions are going to occur. And if certain lines are congested and the transaction cannot occur, then it will send a trading adjustment to the lower level. These entities will take this trading adjustment and then they do adjustment of the transactions and then it goes back. So it's a loop operation between the upper and lower level in order to make sure that ultimately we maximize the profit down here and maximize the reliability up here. So here at the lower level, the peer-to-peer transactive energy is executed. Microgrids trade energy and determine the energy trading price and amount. So all those decisions are made down here. Then we go to the upper level. This signal is sent to the upper level, where at the upper level, the DSO, or distribution system operator, it reconfigured the distribution network in order to make sure that these transactions can occur. So DSO in this case is strictly in charge of managing the distribution network. So in a sense, DSO does not know anything about the price, doesn't know anything about this, who's buying, who's selling. So all that, basically the privacy is managed down here. No information goes up here. So from a sort of a security point of view, all that information is confined to the lower level. The only thing that DSO will do is to manage the distribution wires to make sure that the transaction that is decided at the lower level is physically transactable, and then does it. So I have some equations here. I won't get into that. So at the lower level, we maximize the profit. So this is the utility for profit, the cost, and then the difference between the prices, subject to number of constraints representing the bus balance constraint, generation constraints, load constraints. So here we maximize the payoff at this level, at the lower level. As I pointed out, at the lower level, the intention is to maximize the profit or the payoff for individual participants. So that's done, and then you can use different methods. This is the OPF, optimal power flow solution. You can use the linear programming or nonlinear programming, whatever method you're familiar, mixed integer programming is solved at. At the upper level, the intention is to minimize the trading adjustment. If you recall, I said what is sent down here is the error, which is the trading adjustment. So here the intention is to minimize what goes back. So here we minimize the trading adjustment, where the trading adjustment is basically limited to the level of the flows. So we have the bus, this is the flows, and these are the adjustment at different buses. So basically here, this is another upper level power flow that we solve at this level. So there is one solution here, which is optimization for reliability purpose. There's one optimization here, which is the maximization of the profit, and then these two will exchange information until the solution is managed. The entire problem that I explained earlier could also be done by blockchain. So what is a blockchain? Basically, blockchain can get rid of middleman. So I pointed out that here we have a DSO that is one person that sits here and manages the upper level for distribution management. You can get rid of the person that's up here and then convert it by blockchain. Let me give you an example. For instance, when you go to the bank, if you're going to send some money to a friend, the way it works is that you go to the bank, and then bank is a middleman. You put the money into the bank, and then you use the bank system to send money to your friend. So in this case, the bank system is a middleman. Using a DSO, you get rid of that middleman. So if you want to send money to your friend using DSO, there is no middleman, there is no bank anymore. There's a system that you create a smart contract pointing out that you're sending money to your friend. Your friend identifies that he's going to receive money, and then the blockchain makes the connection between the sender and the receiver. Other example is, for instance, if you're going to sell your house. In this case, you usually have a realtor. There is a person in the middle that makes the connection between the buyer and the seller. If you use a blockchain, you can eliminate that middleman. So if you're going to sell your house, you put that as a smart contract in the blockchain. And then people who are looking to buy a house use a blockchain to find out how many houses are up for sale. And then when they find out that your house is up for sale, they see the price using this, the public and the private keys. And then they send you an offer, a counter offer. And then you guys negotiate, and then finally through the smart contract, one sells the house and the other person buys the house. So in that case, the blockchain, which is a security entity, makes sure that the transaction between the buyer and the seller is done in a very secure manner, so that no other people know who's buying and who's selling. And then ultimately all the decisions are made without the intervention of a middle person. So in this respect, here, as I pointed out, you have the DSO as a person sitting here. You convert that to a blockchain that does the job of the DSO. And then also we had a master controller. If you recall, I said that we have a control room at our microgrid. And then so each microgrid comes with its own control person. We can convert the control person to a blockchain as well. So blockchain in microgrid 1 talks with the blockchain in microgrid 2 using these smart contracts. And then once the decisions are made, who's going to buy, who's going to sell, and then those are finalized, you send the information to the upper level blockchain that clears the signal from a reliability point of view. So all that information in the form of data blocks and smart contracts are done without the intervention of the human beings. All of that is done through the blockchain. And the use of blockchain is needed in order to make sure that these transactions are secure, so that they are not hacked or they are not taken advantage of. So again, in this case, you have a DSO blockchain. At the lower level, you have the microgrid blockchain. So this is the traditional model at the lower level, where these microgrids talk to each other using bids and offers. Now it's converted to using the control entities. Now it's all converted to blockchain. Blockchain in microgrid 1, microgrid 3, microgrid 2, and then these entities talk to each other using private and public keys and smart contracts. So it's a great idea, because using these public and private keys, this operation of this blockchain and the interchange between the microgrids is done in the most secure fashion, so that nobody can take care of that or take advantage of that. Likewise, at the upper level, the DSO blockchain, these transactions, the coordination between the upper and lower level, are done through these, if it's a traditional model, you have the equivalent load coming back up, and a trading adjustment coming down. All of that is converted into public and private keys and the smart contracts using blockchain, and all the interactions are done without the intervention of the human being through the blockchain. So great technology that really allows these entities to do intervention and transactive energy and peer-to-peer transactions using machines without the intervention of individuals. So in this case, the DSO will submit trading adjustment as smart contracts was pointing out. So the trading adjustment that was sent by the human operator here to a human operator down here, from this machine to this machine using smart contracts. One of the projects that we are doing now is to use this blockchain technology for carbon trading. So then, for instance, in your city, one city, for instance, city of Jeddah can do carbon trading with the city of Riyadh, for instance, or other cities nearby. In that case, if there is a limit on how much carbon cities can produce, if one city wants to increase its production, it has to purchase carbon allowance. So in that case, this trading of the carbons are done between the different cities and the usage using blockchain. So rather than one city talking to another city using human beings, all this is done through the machines and in a most secure manner using blockchain. So this is a project that we have, a funded project that we are working on, which is basically done through the blockchain. So in a sense, in the case of a blockchain, you still have the power network here. You still have the market, the financial network up here. This blockchain that comes in the middle to make the financial part connected to the physical layer, like what we did here earlier in the case of a two-level operation. This blockchain allows these two entities to be linked. And it allows the two entities to be connected using a machine without intervention of the human being. So great technology that allows the market operation connected to the physical operation in a most secure and a cyber-secure fashion. One other thing that I'd like to bring up as far as this distribution grid and distributed power system before I conclude is in the case of operation in the emergency case, because so far a lot of things that I pointed out in the case of blockchain and all of that was for the purpose of enhancing the security when two entities communicate with each other. But one thing that's very important, especially in some parts of the world, like in the United States, when they have earthquake, when they have forest fire in the California area, when they have a lot of hurricane in the state of California and the southwestern part of the United States, southeastern part of the United States. For instance, this is one example of hurricane. You can see that when the hurricane hits, like Puerto Rico and some other islands in the southern part of the United States, it really devastates the area. And all the statistics have pointed out that only parts of the system that remain in operation and they're manageable are the ones with microgrid, in the sense that when the system is devastated, you island that operation and then utilize whatever resources you have. These resources could be local in the form of solar or wind or geothermal or batteries. And also it could be in the form of mobile resources, for instance, trucks that bring power to your microgrid. All the statistics have demonstrated that areas that are sustainable are the areas that have microgrids. So here is the functionality of the system. So here, this is without a microgrid. Here the system is a normal operation. And then this is where the major outage occurs. Then this is the sort of a sustained operation in the case of a major outage. Then you rebuild the system, and then you bring it back to the normal operation. So system goes through this, we call it a bathtub. It looks like a bathtub operation that shows how we go from one normal operation to another normal operation. And that's what's shown here. So this is the normal operation, which is up here. Then you go through one degradation, which is this one. Then you are on outage, which is here. Then you rebuild the system, which is here. And go back to normal operation, which is up here. So this shows different stage of the system here. Now, this is without microgrid. Now, when you build a microgrid, you basically eliminate this outage portion, or at least eliminate the total outage. So what you do is that your system is going to have either partial outage or no outage. So this is the system with microgrid. You are in normal operation, you go through degradation, this outage is converted to sustained operation, and then back to normal. And that's what's shown with this red one. So here, as you see, the sort of functionality of the system is enhanced. Before, the system functionality dropped from here to here. And now it drops from here to here. So basically, the functionality of the system is improved. And also, the duration of the outage is dropped. Duration used to be from here to here. Now it's dropped from here to here. So as you see, the duration is shorter, and also the functionality is improved. So that's the benefit of the microgrid. And then if you're lucky, and then if your microgrid is strong enough, you may not even have this degradation. You may have, you go from here to here. Basically, you sustain the operation of the system. This shows a case where you have to do some load curtailment because you don't have enough power generation. So in a sense, microgrid allows you to do a lot, and a lot for managing a system, both from economic point of view and from reliability and from the sustainability perspective. So then stages are divided into pre-outage, responsiveness, which is the during the outage, and then recovery, which is after the outage. So you sustain the system, basically you rebuild the system, pre-outage, during the outage, and after the outage. So the question in the case of a dynamic islanding, this is the last part of my presentation, is if you have multiple microgrid, as I was telling you before, if the system is an outage, then what's the best way of managing these, let's say, 4 microgrids? One option is that convert all of this into one island. So in this case, these 4 microgrids talk to each other, interconnected, like what we had in the case of Chicago. The other option is to divide it into 2 islands. Island number 1 allows microgrid 1 and 2 talk to each other. And then island number 2 allows microgrid 3 and 4 talk to each other. And then these 2 microgrids are interconnected. Option number 3 is that each one of these is one island. So this is island 1 representing microgrid 1, island number 2 representing microgrid 2, and then 3 and 4. And then interconnect these 4. So which one of these 3 options are the best for managing the system when the local distribution system is out? So this is called a dynamic islanding. Each one of these 3 options has its own feature. So this may be better than this, or may be better than this, depends on the circumstance that you have. So in this case, the islanding scheme could be adjusted on an ongoing basis. So depending on when this happens, whether the islanding is 2 o'clock in the afternoon or 8 o'clock at night, this option could be better than this one, or this one could be better than this one. So it's a dynamic process. So the way it works is that we do a 2-stage. At the upper level, we decide what's the best option, and then we implement it at the lower level. And then if this solution is not satisfactory, we go back. So it's a loop operation that allows you to come up with the best. Again, this is another advantage of having microgrid, that you can not only can you maximize the operation of individual microgrids, you can also maximize the operation in the case of a multi-microgrid. I'd like to conclude by pointing out that we are also expanding this notion of microgrids to cover other infrastructures. Cities in the world are getting a lot more crowded. See, traditionally in 1950, about 1 billion people, which included 30% of the world population, lived in big cities. Expectation is that by the year 2050, about 70% of the world's population are going to live in big cities. I'm sure it's happening in your country. You can see that cities are getting bigger because people are moving to big cities. We see it a lot in countries like China. We see it a lot in countries like India, in Bangladesh, in Pakistan, where people are moving into big cities. And moving to big cities creates a mess like this. Cities are getting a lot more crowded. Creates a mess like this. Look at the level of the pollution. Look at the level of the water pollution in other parts of the world. So this urbanization is a critical issue because of this variation. But we need to deal with that. So the notion of the smart city, I gave you the example of the electricity so far, but that same thing can occur in the case of water, can happen in the case of a city pollution, transportation pollution, that we need to sort of introduce these migration and distributed systems in order to be able to manage all of these. So the point is that traditionally, for instance, when I studied electric power system, when I worked with other entities and we worked with utilities to study electric power system, I assumed that the oil, transportation, gas, telecommunication, all of these were available. But now that we are looking into smart cities, we can see the link between these. So the point here is that when I study electric power system, I cannot only study electric power system in a smart city notion. I still have to look into transportation, gas, and all the other entities within the city in order to come up with a comprehensive modeling of a smart city, whether it's distributed or centralized, in order to come up with a system that's a lot more sustainable, secure, resilient, reliable, and economically managed. This was my last slide. I'm going to stop here, and I'll be very happy to answer any question that you may have. I hope you enjoyed my presentation. Thanks.
Thank you very much, Professor Mohammad. It's really great and insightful talk. Me myself, I've learned a lot of things that that wasn't in my mind actually about microgrid systems and all the system that you can create within the microgrid system. Thank you very much, Professor, and would actually like to open the floor for any questions from the participants, any of the attendees. Anyone has any question, please, you could raise your hand if you want, just to go to on the participant list. And, or if you want, you can just go ahead and unmute your mic and tell me the questions. I haven't got any questions in the chat so far, but if you have any questions, go ahead.
You can ask me whatever question you have. Don't be bashful.
Right. So I have a question. So I do research in transaction processing and blockchain systems. Have you experienced any shortcomings? Because okay, so let me just give some context. So you talked about blockchain technology as a black box. So in order to realize this vision of the transactive energy markets, do you see any shortcomings of the current blockchain technologies that maybe raises challenges for efficient realization of the transactive energy markets?
Certainly. The sort of shortcoming predicaments are numerous. For instance, as you know, blockchain is a very time-consuming, it's like a Bitcoin. It's a very time-consuming process. So there are people, companies in the United States, and our colleagues in computer science departments in various universities here in the US and elsewhere, and I'm sure in your country, people are working on making blockchain a much faster process, and also to a process that's not consuming so much energy, so much money, basically, to do the process. And then, as you know, because electric power system is a system that has its own grid, of course, the way we set it up here, and I explained that, we sort of come up with the two systems in order to separate what the blockchain is doing for, let's say, transactions between microgrids, separate from the electric power system, the grid part of it. But still, it's a two-stage process. So the existing blockchains may not exactly apply to electric power system. So there is quite a bit of research going on in order to make that possible. So yes, now this is just the beginning. It's a lot of work for people, researchers, investigators in various universities, and also companies that are looking into producing new products in the form of blockchain and other technologies like transactive energy. It's just the beginning. There's a lot of work needs to be done, certainly.
Great, wonderful. Thank you, Professor. Any other questions? Please go ahead.
I have a question, please.
Go ahead, Mr. Nasser.
Thank you, Dr. Mohammad. I'm Nasser Anizi. I gave a master's with Dr. Kodai. Absolutely, you know him. My question is, what's the best method to increase the resiliency for the microgrids?
Yeah, as you know, let me point out that you refer to resilience. Let me point out that there is a difference between resilience and reliability. As you may know, reliability is something that can happen every day. For instance, you may lose a transformer in the distribution grid. You may lose a generation in the transmission grid, but that can happen any day. So basically, reliability refers to high probability with a low impact. Like if you lose a transformer, there's a great chance that it can happen, but its impact is small. In particular, if you have an N-1 type of operation, your system will not even see its impact. Whereas reliability refers to low reliability, high impact. For instance, fire. For instance, earthquake. Earthquake doesn't happen every day. Fire does not happen every day. So its probability is very small, but the impact is significant. For instance, if you have fire in the city, it could damage several neighborhoods. So its impact is significant. So that's the difference between the reliability and resilience. Now, your question is, how do we solve the issue with the resilience? The solution for the resilience is sort of customized for the type of issue. For instance, if the resilience is related to fire, the solution could be very different than if the resilience is related to earthquake, if the resilience is related to tornado. So what we have done is that we have come up with specific solutions for the type of the disaster or the extreme event that's out there. And also the resilience solution that you come up with, let's say for the city of Jeddah, could be very different from the resilience solution that you introduced, let's say in the city of Riyadh or another city, or if it's for the village. The resilience solution could be very different. So resilience solutions are customized depending on the type of the outage and the location of the outage. But the technologies, it varies. For instance, you can introduce different microgrids. In some places, the microgrid could be stationary, meaning that, for instance, you convert the university, the KAU, to a microgrid. Also, there have been cases where the solution is mobile. For instance, you could put a generator on the back of a truck. And then depending on where the outage occurs, you can dispatch the truck, and the truck could go there, and since it's a generator on the back of the truck, you could generate electricity, for instance, for the police station or for the hospital or whatever load you have to supply that. So solutions vary depending on the location and depending on the type of the outage. And it's very difficult to come up with one generalized solution that applies to different systems. I hope I answered your question.
Yeah, I got it. Thanks.
Sure.
Thank you, Nasser. Thank you very much for the question.
Sure.
There is another question here in the chat. Mr. Ahmed Fatan asks, what is the first important step to applying the multi-microgrid circuit?
The question was, where is it, you said?
What is the first important step to applying multi-microgrid?
Sure. Well, let me start with what's an important step to build a microgrid. When you want to build a microgrid, there are certain stages, like the microgrids that we built. The first step is to study what you have available. In a sense, the microgrid that you build at KAU, for instance, or the microgrid that you build in a hospital, or if you convert a palace to microgrid, the solutions could be quite different. So what you would have to do first is to see what's available, what kind of a load you have at that location. For instance, if it's a hospital, what's the load profile? Is the load fixed for the entire day? Do they have the peak load? What's the load profile, let's say, in a daily basis? Is it summer peak? Is it winter peak? So you have to do a study first based on what kind of a load you have, how many critical loads you have. The second thing is what kind of generation is available. If it's, for instance, palace, or if it's a hospital, or if it's a university, does it already include some kind of generation? Is there a local generation that already in existence? And then how much of the load that generation covers right now? And then what's the state of that? Is it in a good shape? Is it in a bad shape? How often it's been maintained? Also, you do a study on the existing grid within that operation. For instance, if it's applying to this police station or a hospital or a university, what kind of a grid is that? How secure is it? How old is the distribution grid? So you do a sort of a study on the grid sort of it. So you study on the generation and distribution and also load. Once you do that, then you identify what's the objective of building a microgrid. Is the objective economics? Objective reliability? Is the objective security? Is the objective resilience? For instance, if I build a microgrid in one of those islands, the objective is not economics. The objective is the resilience, so that if they have a hurricane, people can still stay alive, use the electricity. If I build a microgrid, let's say at KAU, it's possible that the objective is reliability, not the resilience. So you define your objective, and then based on that, you start building a microgrid. Because I know my objective, I know the state of the system, and then I start building it. So first you put together a plan for building a microgrid, and then you start implementing that plan depending on how much money you have available. So if you have all the money available, you start building a microgrid right away. If the money is coming annually in stages, then you build a microgrid in different stages. So the same thing applies to network microgrids, that you come up with a design for individual microgrids, then you decide how you're going to network depending on what's the purpose of networking a microgrid. Are you networking a microgrid for reliability reasons or for economic reasons or what else? So based on that, you figure out how these microgrids need to be networked and how secure that network would have to be. I hope you answered your question.
Okay, yes. Great, thank you, Professor. So we will have one more question or two more questions. If anyone has any more questions, and conclude, inshallah.
Yeah, let me know if there's more questions.
Yeah.
Assalamu alaikum.
Assalamu alaikum.
Yes, Professor, thank you for this insightful presentation. My question is, within the blockchain and the model you created, what would be the data exchanged within the blockchain? Is it the money or the contracts, information, the tariffs?
Yes. So let me go back to this model that we had here for the blockchain. It depends on whether the blockchain is within the microgrids or the blockchain is between the microgrids and the DSO. As I pointed out, we have two blockchain. One is between the DSO and the microgrids, and the other one is between the microgrids. If it is between the microgrids, the smart contracts includes two. One is the value that you're willing to transact, value of the power, and the second one is the price of the power. So the smart contract that you write points out that similar to here, that you had bids and offers, here, for instance, blockchain number 1 indicates that I'm willing to sell 1 kilowatt of power at this price. This guy points out that I'm willing to buy power, these many kilowatts of power I'm willing to buy at this price. So this smart contracts that goes back and forth is based on, I mean, this person puts a smart contract in, pointing out how much he wants to sell, and this guy puts the smart contract in as to how much he wants to buy, and then the blockchain basically matches the two, and then decides who's going to buy and who's going to sell. So once it's done, then the transactions will occur. So in this case, the transaction between these two would be the amount and the price. The block of data that goes between these two, there is no price involved. In this case, this entity basically says that how much it's going to buy or how much it's going to sell. This guy will indicate how much he's going to buy and how much he's going to sell. So basically, the blockchain up here receives the information as to whether this is a sink or the source. Sink means it's going to buy power. Source, it means it's going to sell power. Same thing with this one, whether the blue one is the sink or the source. So once the DSO, which runs the OPF, in this case, I mean the blockchain DSO, knows what the sinks and the sources are and has the information on the grid, it figures out whether these sinks or source can be interconnected using the existing grid. So if it is possible, it will do it. If not possible, then it will send a smart contract pointing out that transactions cannot occur because for instance, there's congestion in the grid or the voltages cannot be satisfied. And then using that smart contract, in the case of a smart contract, for instance, here, these guys down here don't know anything about the voltages or the state of the distribution grid. All they receive is in the form of a smart contract that helps them modify what they're doing down here. And again, this will happen. So using this blockchain and using these smart contracts that are provided either through the DSO or through these individuals that are transacting energy, then these guys will buy and sell electricity or modify their initial transactions in order to make this entire system work. So one of the things is that by separating between these lower level and upper level, you manage the security of the system. In a sense, at the upper level, you only manage the transmission and distribution data. So the DSO, which manages the information on the grid, does not have to share the distribution grid data, basically the wires, with the lower level. Likewise, at the lower level, where these guys handle the money, they don't have to share any information about the money with the upper level. So basically, the security at the lower level and the security at the upper level is totally managed within their respective blockchain.
Thank you.
Sure.
Professor,
Go ahead.
Yeah, thank you so much. Beside the housing market you mentioned, what other markets have you seen going to implement the blockchain in their regulation?
Oh, blockchain is actually applied much more comprehensively into the financial markets. So blockchain is used right now as we speak between these entities. I mean, of course, here we're talking about like microgrids, but this could be bank number one, bank number two. Right now, blockchain is used a lot in the financial industry in the United States and elsewhere. And also, we have seen the use of blockchain a lot in the healthcare industry, for instance, between the doctors and the patients. So that way, you can send your information without sort of introducing the patients between the doctors, or sending it between the doctor and the patient without introducing the doctors and that sort of things, where the issue of the privacy and issue of the security is a critical issue. So right now, a lot of that information is done in the areas where the patient privacy, financial security are very, 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 very important. And then now we are trying to use that in the electric power industry, where the information, let's say for the grid, cannot be shared with individuals, or individual participants don't want to share their information, for instance, how much you want to sell, what price you want to sell, with the upper level. So the use of the blockchain, and you may have heard that the blockchain in the sort of Bitcoin has taken over. A lot of people are participating in that application.
Thank you, Professor.
Sure.
Take quite a long time, but there's one last question that was sent to the chat from Omar Hafiz. After thanking you, Professor, for the informative webinar, he is asking, is there any study regards the subsynchronous resonance, SSR, in brackets, with microgrid?
Well, the subsynchronous resonance and all of that are very sort of a grid-related issues. So those are some of the issues that are done at this level, in the sense that the DSO looks into, if you divide the system into these two levels, at the lower level of that, these entities don't have to worry about it. Now, within my one microgrid, the master controller of this microgrid may do issues like subsynchronous resonance and voltage issues and stability issues and reliability issues within microgrid one. But you don't have to share the information between these two entities. At the DSO level, because the DSO is in charge of the grid, DSO does a lot of, let's say, the grid studies and harmonic studies and subsynchronous studies and voltage studies and all of that, again, confined to this level, but that does not have to trickle down to this level. So yes, all the traditional power system studies that you're familiar with and you're interested will be done at this level. You could also limit it to within each microgrid, but does not have to be transpired within the microgrids.
Okay. All right. I think we've answered all the questions that came up here. And at the end, I would like to Professor for this wonderful talk, this project and ideas that actually could open up a lot of opportunities for many specialties, not only power systems, power engineers, but also many other could contribute into this project. And it's really, really useful and a noble idea, actually. Thank you, Professor. Thank you very much for your time and for your talk. I would like to thank Professor Ahmed Abdul Wahab for organizing this and for giving us the chance and the opportunity to meet you and to have you with us. I would also like to thank IEEE Western Cybersecurity section and the Saudi Council of Engineers, especially the Ieee chapter of this SCE for hosting and organizing this webinar as well. And I would like to thank everyone that attended this seminar and registered and was actively participating in this webinar. Thank you very much for attending, and I hope that you all got some useful information and some insightful ideas from this from Professor Shahidehpour talk. I will also list the your personal page and the IIT website, Professor, here in the chat. So for everyone here to see it, and maybe if they have any more questions or have wants to learn more about this project or other research topics that you're working on, please go ahead and visit this website. And at the end, thank you very much for everyone. Thank you for your talk, Regan, and would be more than happy to see you, inshallah, here in Jeddah if you have a chance. And also maybe we might have some other seminars if your time as allows as well. So thank you very much. Everyone.
Thanks.
Thank you.
Thanks. Bye-bye.
Bye-bye for now. Thank you very much. Assalamu alaikum.
Assalamu alaikum.